All right, hi guys. We are starting on Unit 9 today, which we're going to look at some simplifying radicals, dealing with roots of real numbers, and then also we're going to start talking about imaginary numbers in this unit. But today we're just going to focus on some kind of algebraic simplifying of square roots and of cube roots, which is new for us this year. We have done some simplifying with square roots. Normally we review that in the last unit, but this year's just different. So we're going to kind of go over that first, but just kind of going through some stuff in this unit that we need to have in our skill sets so we're ready for some stuff coming up. Okay, so starting with square roots. Kind of get a definition here. A square root of a number is a solution to an equation x squared equals some number. Every positive number has two square roots. One of them is the positive square root, one's the negative square root. The positive square root is also always called the principal square root, so sometimes you'll see that. So if you ever see principal, you know that means the positive. But basically all this means is that if I have something like x squared equals 4, if I want to solve that for x, well then x would equal the square root of 4, which means that x equals 2, right? But when we're solving, we don't know if we want the principal square root or if we want the negative square root. So we've talked about this in the last unit. This is why we use that plus or minus sign. There's also a possibility that it could be x equals negative 2. So that's why we've got two square roots, right? That's why it says that up here. We've got both the positive square root and the negative square root. If we are taking the square root of a negative number, so I have something like x squared equals negative 4, we've talked about this as well. If I take the square root, I get x equals the square root of a negative. That doesn't work. I can't multiply anything times itself to get a negative, so that's why we say there is no real root here. Towards the end of this unit, we'll kind of talk about how to deal with that, but we'll get there eventually. Okay, a couple quick examples here that we know. If it's just a number, if you're just taking a square root of a number, you don't have to worry about the plus or minus. So this first one, if I want the square root of 9, because that is just the square root sign, that means I want the principal square root, so our answer is 3. This one has a negative in front. That means I want the negative square root, so this answer would be negative 3, right? Difference is up here, we were doing x. If I'm doing the square root of something and I don't know if I want the positive or negative, we give both possibilities. But if you're told, if it's just a number like these, principal or negative square root, then you know which one. Remember, if you've got a fraction inside of your radical, you can split that fraction. So this is like the square root of 1 over the square root of 9. And then those are both the principal square roots. So I can do those. They're both perfect squares. Square root of 1 is 1. Square root of 9 is 3. So our answer there is 1/3. If you've got a decimal inside of a radical, it helps to make that a fraction. So if we read that number, that is 9/100ths. So I'm going to change this to 9 over 100 and do the square root of that. And remember, again, I can split that. So that's like the square root of 9 over the square root of 100. Those are both perfect squares. So we get 3/10, or if you wanted to change it back into a decimal, that'd be 0.3, right? So either of those answers, okay. So just a couple reminders on square roots there. Okay, so one thing that is a little bit new for us, we haven't talked a whole lot about cube roots of numbers. With a cube root of a number, there is only one root, because when I'm doing cube roots, I can get a negative or a positive, right? So for example, if I've got x cubed equals, we'll do 27, right? If I take the cube root of both sides, I do x equals the cube root of 27. Remember, the cube root means what do I multiply times itself 3 times to get that number? Well, if I do 3 times 3 times 3, I get 27. So the cube root here is 3, right? If I look at a negative number, if I do x cubed is negative 27. I think about that this time. And I do the cube root of both sides. So then I get x is the cube root of negative 27. Because now I'm multiplying something times itself 3 times, I can get a cube root of a negative number. Because if I do a negative times a negative, that gets me a positive. But then times another negative would make that number negative. So this answer would be negative 3. Right? Over here, this is like 3 times 3 times 3. And on this one, negative 3 times negative 3 times negative 3. So when you've got a cube root, you can have a negative inside that radical. So a couple examples here. If I want to do the cube root of 8, what times itself 3 times would make 8? By the way, there's also a button on your calculator. I'll kind of help you guys out with that in a bit when we need it. But you won't need it too much here yet. But what times itself 3 times make 8? This would be 2. 2 times 2 times 2 is 8. The next one, this one we kind of just talked about, the cube root of negative 27. Even though there's a negative in there, we can do it because it's a cube root. So the answer here would be negative 3. If I want the cube root of 10 to the 6th power, again, I'm looking for what can I multiply times itself to get 10 to the 6th. I'm going to focus on that exponent. If I do, when I'm doing exponents, remember when I multiply the bases, I would add the exponents. So I could rewrite this as the cube root of 10 squared times 10 squared times 10 squared, right? Because 2 plus 2 plus 2 would get me back to that 10 to the 6th. So since now I have 3 of those, that means the cube root of 10 to the 6th would just be 10 squared, which is 100. Okay. Same thing with our variables. We'll kind of do the same idea. We're looking for what times itself 3 times would give us a to the 9th. And one good way to look at this is you can always kind of take that exponent and divide by your index on the radical. We'll talk more about that in the notes today. But really what I'm doing here is I would have to do a cubed times a cubed times a cubed, right? Because 3 plus 3 plus 3 would give us 9. So then the cube root of a to the 9th would be a cubed. Okay, I'm going to pause here for a second, answer the quick question, and then we'll come back. All right, next page here, we're going to talk about the nth root. So we talked about just the square roots and cube roots, but you can do more than that. You can do the 4th root of a number, the 5th root of a number, 6th root, and so on, right? I can make that index on our radical be whatever number I want to. So there's a couple rules with this based on whether that that index is positive or negative, okay? And based on the number that's inside the radical. Okay, so our first case here, we've got if n is even and b is greater than 0. So remember, look here, n is going to be the exponent or the index that is on our radical, and b is going to be the number that's inside the radical. Okay, so another way, let's write this way. So really I'm looking at the nth root of x. The nth root of b would equal x. Okay, so that kind of tells you what n and b are there. So if n is even, the index on our radical is even, and b is greater than 0, meaning the number inside the radical is positive, we get 2 real roots. Okay? If I want the 4th root of 81, what times itself 4 times will give me 81? Well, it could be 3. This is x equals, right? So x could be 3 because 3 times 3 times 3 times 3 is 81. Or it could also be negative 3 because negative 3 times negative 3 times negative 3 times negative 3 is 81, right? All right, our next case, now we're going to say that n is still even, but this time b is equal to 0. Anytime, it doesn't matter what root I take of 0, you're always going to get the same answer. It's always going to be 0. So this one just has one real root. And that root is always going to be 0. Okay? No matter what your index is, you're always going to get 0 there. Okay, our next case, now we've got n is still even, so our index is still even, but this time our number inside the radical is negative. That's always going to mean that there are no real roots. We can't take an even index radical of a negative number. So this we just write for our answer, no real roots. And again, there are roots there, they're just not real. We'll talk about that later. All right, and then our last case is if the index is odd, right? So if our n is odd, just like we talked about with the cube root, here again, there's always going to be one real root. And it doesn't matter if the number inside is positive or if the number inside is negative, because when we multiply an odd number of numbers, we either get a positive or we get a negative. If I have an odd number of positives, I get a positive. If I have an odd number of negatives, I get a negative. So the fifth root of 32, what times itself 5 times will give us 32? Well, this one would be x equals 2. 2 times itself 5 times is 32. And then this one, if it's negative 32, then we get x equals negative 2. Okay, so just think about what the index is. If it's even, you have these 3 different possibilities, right? We could have 2 roots, we could have 1 root, we could have no roots. If n is odd, you're always going to have just 1 root based on what the sign of that number inside is. Okay. So now let's kind of look at a few properties here of radicals just to remember. We've talked about a couple of these before. One of them is a little bit new, and we'll kind of see how that works. So the first one is that you can, anytime I take or square a square root, that kind of undoes that operation. If I cube a cube root, it undoes that operation, right? So in this one, if I'm doing the nth root of something to the nth power, I basically just get whatever's inside the radical left over. We did this in this last unit. If I was doing, we talked about like where we had x minus 1 squared, right? If I then take the square root of that, then I just end up with x minus 1. Or the same thing works. If I have the square root of x minus 1 and then I square that, then I just end up with x minus 1, right? Those things, those two operations undo each other, or inverses of each other. Okay, so for example, we could write, if I've got the cube root of 8 and then I cube that, that is going to give us 8. Right? You can think about the cube root of 8 is 2, and then 2 cubed is 8. Okay, our next two, these have more to do with our variables, but we'll look at some number examples with how these work. Okay, so if your index is odd, right, then when you take the nth root of something to that same nth power, then you just end up with that same thing. So if I have the cube root of x cubed, then we just get x, right? And we can kind of look at an example. This is what we just did above, right? If I'm doing the cube root of 8 cubed, we just get 8, right? That's what we just talked about. But if I do the cube root of negative 8 cubed, then we end up with negative 8. So you can see how if I had 8 here to start, I ended up with 8. If I had negative 8 to start with, I ended up with negative 8, right? Those matched up. So this property here works when n is odd, right? Now, if I switch that and I talk about n being even, there's kind of a special little case we have to think about. Now we're going to need some absolute value, and I'll show you why. So this one, for example, if I had the fourth root, if our n is even, right, this time it's even, of x to the fourth, that's going to equal the absolute value of x. Here's why. If I were to do the fourth root of 2 to the fourth power, right? Well, this one works just fine. 2 to the fourth power is 16, and then the fourth root of 16 is 2. That one works just fine. Now, if I do the fourth root of negative 2 to the fourth power, well, when I do negative 2 to the fourth power, I'm multiplying something times itself an even number of times, which means I'm going to end up with a positive number. And then when I take the fourth root of that positive number, I still get a positive. So in this case, no matter what we do, we always end up with a positive out there. So even if I plug a negative number in for x, I end up getting a positive number as our answer. Because of that, this is why we have to use absolute value when that index out there is even. Okay, so those can get a little bit tricky. They take practice to get used to. I'll keep reminding you guys on these, and we won't test it a whole lot, but you do need to know kind of the basics of this. Okay, so here's a couple examples. If I've got the square root of x squared. Okay, so even though that index is not there, remember, that means that that's a 2 for our index. So this is an even index, right? I have an even index on this one. Let's write this over here. Even index, and I have an even exponent, right? If they're both even like that, you need absolute value. So the square root of x squared is actually the absolute value of x. Okay, the next one, we have the square root of x to the fourth power, right? So this time again, we've got an even index, and we've got an even exponent. Okay, but this time when I do the square root of x to the fourth, I'm looking for what times itself makes x to the fourth. I'm going to get x squared, right? Now, normally I'd say, well, this means we need absolute value. But if our answer is x squared, whatever we plug into that is going to get squared, which means it's going to end up positive anyway. So on this one, we don't need absolute value. Okay, let's look at one more here. Again, we've got an index of 2. So this one again has an even index, and it has an even exponent. And this time when we do it, when I take the square root of x to the 6th power, so what times itself makes x to the 6th? Well, that would be x cubed. So again, because it's an even and an even, that means we need absolute value. And this time, because it's x cubed, if I were to plug a negative number into that, I'm going to end up with a negative, which because of this property up here, I don't want that to happen. When they're both even, when our index and our exponent are both even, it's always going to end up a positive. So I need to put absolute value here. Okay, so on those three, the big difference here is that this exponent, when we end up with our answer, see how these two have odd exponents in the answer, but this one has an even exponent in the answer? That's the difference, right? So this one, the answer has an odd exponent. And this one, the answer has an odd exponent. But this one, the answer has an even exponent. When you see the odd exponent, that means we need absolute value. So these two, odd exponent, we need absolute value. With the even exponent, you don't need it. You're good. Okay. Okay, so our next few, let's kind of look at the same thing here, but this time our index, we've got a couple different indices or indices. This time on these two, our index is odd, right? So I've got an odd index and an even exponent. In this one, I have an odd index and an even exponent. Right? Since our index is odd on these two, we don't even have to think about the absolute value. It doesn't matter, right? You only have to think about that on the even index. So for these, I just want to know what times itself 3 times would give me x to the 6th. So that's going to be x squared. And because, again, that index is odd, I don't have to worry about absolute value. The next one, what times itself 3 times again, will give us x to the 9th. Well, that would be x cubed. And again, because our exponent or our index is odd, we don't have to worry about absolute value. Okay, this last one, we go back to an even index, right? But this time, and we also have an even exponent. So this time we are going to have to think about if we need absolute value. So I want to know this time what times itself 4 times would give us x to the 12th. If you haven't figured it out yet here, remember again, you can always take that 12, divide by that x or that index, and that gives you the answer there. So this would be x cubed or x to the 3rd. So here's that one again where our answer has an odd exponent. So that means we need absolute value, right? So this one, I've got to put in absolute value. Okay, so really the trick here is if you have an even index and your answer ends up with an odd exponent, you need absolute value, right? So let's kind of write that down here on the bottom. So if we have even index and the answer has an odd exponent, then we need absolute value. Okay, that's kind of the important thing to remember with these. By the way, this is only with variables. If you're dealing with numbers, you don't have to worry about any of this. This is only if there's variables in the radical. Then we have to think about that rule. Okay. All right, I'm going to pause here again for a quick question. So answer that, and then you can come back. All right, this next section here should be review. We've actually talked about this before, but it's been a minute. So we're going to do a quick little review of this. This is our rational exponents, right? So again, here, the important thing to remember is this stuff right here. And basically what it means is that if I've got an exponent that is a fraction, right? Remember the top number is your exponent, the bottom number is your index, right? So if I have, I'll just make an a over here, a to a fraction exponent, it's always the exponent over the index. When you change it into this, when we talked about changing it into exponential form versus radical form, right? So in this, oops, I didn't mean to erase all that. In this guy here, this one is exponential form. And then both of these are radical form, right? That should be obvious. There's radicals in there. You can do it either way. So just notice these two things are the same. It's just about whether you put the exponent inside the radical, or you can put the whole thing in parentheses and put the exponent outside the radical. And I'll kind of show you that in the examples. Okay, so let's look at one here. If we wanted to simplify these, I've got 25 to the negative 3/2. Well, before I deal with the fraction here, I'm going to deal with that negative and fix that. Remember, to fix a negative exponent, we move it to the opposite side of a fraction. So I'm going to change this to 1 over 25 to the positive 3/2, right? Make sure again, and I may write this a little bigger so we can tell, make sure when you write your exponent down here, it should look like an exponent. Don't write it as 25 and 3/2. That looks like a mixed number. Okay, make sure if it's an exponent, it's up higher and it's smaller like an exponent. Okay, so then to change this or to simplify this, it's going to be much easier to simplify if we put this into radical form. So now we're going to change this. We're going to keep the 1 on the top. And then the 25 is what we put inside of our radical. And then remember from over here, we've got our exponent on the top. Our index is on the bottom. An index of 2 just means we want the square root. So that'd be like here, but I don't have to write it if it's a 2, so we don't need it. And then the 3, I can either put the 25 cubed there, but if I do 25 cubed, that's a pretty big number. I don't want to mess with that. So instead, I'm going to put the whole thing in parentheses and do my cubed on the outside. So now when I go to simplify, well, I can do the square root of 25. That's a perfect square. So it would just be the 5, and then I still have the cubed. So then 1 over 5 cubed is 1 over 125. Okay. So change to radical form, then you can simplify. Same thing with our other one. We'll do an example here. We've got 9 to the 2.5. If you've got a decimal, remember you can change that into a fraction. This is like 9 to the 2 1/2, right? I don't want to keep it a mixed number though. Let's make it improper. That will make it much easier to do our exponent and our index. So then I'm going to write this as 9 2 1/2 would be 5 halves, right? So now I'm going to change that into a radical form. So I'll put my 9 inside the radical. Index is 2, so that's like a square root, but if it's square root, we don't have to write the 2. Our exponent is 5. Again, if I put it here, I got to do 9 to the 5th power. That makes a really big number. Instead, I can do the square root first, and that makes it a smaller number to deal with. So I'm going to put the 5 out there. So then the square root of 9 is 3. So that means I need to do 3 to the 5th power. And 3 to the 5th power is 3 times itself 5 times, which is 243. Okay, so if you kind of remember doing those last semester, that's not too difficult there. All right. Next one. Now we're going to kind of look at the same thing, but with variables. I can't remember if we talked about this first semester or not. We may have, but it's kind of the same idea. Now I'm taking something in radical form, and I want to change it into exponential form, right? So remember, we've got that thing here where if it's in radical form, to get it in exponential form, I take whatever it is. Well, let's use a different one here so we know. And then the fraction is always the exponent over the index, right? So for all of these, our index is going to be 3, but then our exponents are different on each letter. Okay, so I'm going to keep it in a fraction to change it into exponential form and just do one variable at a time. So I'll take a here, and it's exponent over index. So I would do 5 thirds, right? 5 over 3. B has an exponent of 3, so it'd be 3 over 3. And then C would be to the 2 thirds, right? And then I can simplify the B because 3 over 3 is just 1. So then we can rewrite that as A to the 5 thirds. B is just to the first power. And then a lot of times you'll see these when we put it in exponential form, some people don't want to keep it in a fraction. So I could then move the C up and make that a negative 2 thirds. Or, we could keep the C on the bottom, A to the 5 thirds, B all over C to the 2 thirds. Just depends on what the directions or what other problem you're trying to do there, but those will both work. Okay. All right, I'm going to pause here for one more question or another one. So go ahead and try that and come back. All right, last type of problem we're going to look at. These can get a little bit tricky, but kind of learning about how these work will help us with the next unit we talk about. Okay, so This time, or this one, we've got two radicals here, and it tells us to write the following in exponential form, and then we want to get it in simplest radical form. So what we have here is we're multiplying two radicals, and if you guys remember the rules with radicals, I can multiply two radicals as long as they have the same number inside the radical. So if I have like radical 3 times radical 3, I can do that and I get radical 9, right? But if I have two different numbers inside the radical, I can't just multiply those. And actually, I'm sorry, it's not that I have two different numbers in the radical, it's that we have a different index on each radical. So this one is a square root and this one is a cube root. So I can't just multiply those two numbers. If it was just radical 8 times radical 4, then I could do that and I could get the square root of 32. But since one of them is a cube root, I can't just multiply those two radicals. Okay, so instead, we're going to use exponential form to help us simplify this. So first step here, like it said, is we're going to write it in exponential form. Okay, so exponential form just means, remember, we're going to give it a fraction exponent, and it's or exponent over index, right? So the 8, I've got 8. The exponent on the 8 is a 1, and the index, even though we can't see it, remember, is a 2. If we don't see an index, that means it's a square root, so it's 8 to the 1/2. Times our 4, the exponent on that one is a 1, and the index on our radical is a 3. So 8 to the 1/2 times 4 to the 1/3. That is the exponential form of this, right? Okay, now to simplify this in exponential form, we're going to try to actually multiply those numbers. Now again, I can't just multiply the 8 times 4 because they have different exponents, right? I would have to deal with the exponent first. So what we're going to do is we're going to change this exponential form so that both of those terms have the same base. So we want to get the same base. And how we do that is by looking at the 8 and the 4. Those are both multiples of 2, right? If they're both multiples of 2, then I can change them to a base of 2. And here's how we do that. 8 is actually equal to 2 cubed. So I'm going to rewrite this as 2 cubed. That replaces the 8. And then all of that is to the 1/2 power. 4 is 2 squared. So I'm going to rewrite the 4 as 2 squared, and that's to the 1/3 power. Okay. Now we can simplify. We're going to use our exponent rules. Anytime I have a power to a power, right, we multiply those exponents. So this would become 2. 3 times 1/2 is 3/2 times, let me make that bigger so it looks like an exponent. So 2 to the 3/2. And then our other one, when I do 2 times 1/3, we would get 2 to the 2/3, right? So that's just our exponent rules. Now that I have them in the same base, when they have the same base and we're multiplying, we can add our exponents, right? So now all I need to do is add my exponents. So I've got to do 3/2 plus 2/3. Get yourself a common denominator here, which would be 6. So I got to multiply the first one by 3. So this would be 9/6 plus this one would be times 2. So 4/6, which gives us 13/6. So then that means I keep the same base. I add my exponents together. So it'd be 2 to the 13/6. This is our simplest exponential form. Right? That's as simple as we can get it there. Okay, now the problem though asked us to put this in simplest radical form. So now that we've got this down to just one number, we're going to put it back into a radical. Right? So now I want to change it into radical form. So I'm going to put my 2 back inside of a radical. right? And then the top number is my exponent, the bottom number is the index. So I put the 6 as the index, and this is 2 to the 13th. Okay, so now I've got it in radical form, but I want to get it into simplest radical form. So I'm going to simplify this. And basically what I need to think about is I have 13 2's inside this radical, right? And if it helps you see it, you don't have to do this every single time. I'm just going to do this time. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I almost ran out of room there, right? If I have 13 2's, if I'm doing the 6th root of that number, then I need to make groups of 6. So I can take 1, 2, 3, 4, 5, 6 of those 2's and make a group. And then I'm going to take another 1, 2, 3, 4, 5, 6 of those 2's and make a group. And I have this one little lonely 2 left by himself, right? So really then I can rewrite this as the 6th root of 2 to the 6th times 2 to the 6th times that 2 that's left over. And if I'm doing the 6th root of something to the 6th power, well, then that's just the number, right? So the 6th root of the first 2 to the 6th is 2. The 6th root of the second 2 to the 6th is another 2. But then I still have a 6th root of a 2 left over. So then that gives us 2 times 2 on the outside is 4 times the 6th root of 2. That is our simplest radical form. I know that problem is kind of a lot, and especially doing it on video notes, but we will get some more practice. There's a couple on your homework like this. Try it. Try at least one part of it, even if you can only get it into exponential form and then you struggle with the next part, right? So make some attempt at it, and then we'll go over those. All right, we'll have one last question here at the end, and then we will continue with these after we finish up tests and stuff this week. So whenever we have our next class after your test, then we will start with notes 2 and some questions over homework 1 on this stuff. Answer the question, and then you're good to go.